Hello, welcome to this short course on Kyber and Dilithium. My name is Alfred Menezes. In 2024, the U.S. government's National Institute of Standards and Technology, NIST, published a suite of standards for key encapsulation mechanisms and signature schemes that are resistant to attacks run on quantum computers. These quantum-safe schemes are intended to replace their RSA and elliptic curve counterparts, which we know can be totally broken by large-scale quantum computers. Of the quantum-safe schemes standardized by NIST, the ones that are expected to see the most use in the coming years are Kyber, a key encapsulation mechanism, and Dilithium, a signature scheme. The purpose of this short course is to give detailed descriptions of Kyber and Dilithium as specified in the NIST standards FIPS 203 and FIPS 204. I should note that the official name for Kyber in FIPS 203 is ML-KEM, which stands for Module Lattice-based Key Encapsulation Mechanism. And the official name for Dilithium in FIPS 204 is ML-DSA, which stands for Module Lattice-based Digital Signature Algorithm. However, I'll use the original names Kyber and Dilithium because they're easier to say. By the end of the course, you'll understand how Kyber and Dilithium work, and you'll be comfortable reading the NIST standards and filling in the technical details that I might have omitted. You will also appreciate the many optimizations that were incorporated into Kyber and Dilithium in order to enable fast implementations and to decrease key sizes, ciphertext sizes, and signature sizes. Kyber and Dilithium are lattice-based schemes, and in particular use certain lattices derived from modules of polynomials. However, lattices are only needed to understand the state of the attacks on the underlying mathematical problems that are the basis for the security of Kyber and Dilithium. Since the primary objective of this course is to understand how Kyber and Dilithium work, and not to give a detailed analysis of their security, I won't explore lattices in this course, let alone define them. The course is comprised of 4 chapters. In Chapter 1, I'll introduce the field of post-quantum cryptography and cover some mathematical prerequisites that are needed for understanding Kyber and Dilithium. I'll present the Kyber key encapsulation mechanism in Chapter 2, along with its underlying public key encryption scheme. In Chapter 3, I'll present the Dilithium signature scheme. Finally, in Chapter 4, I'll describe the number-theoretic transform, the technique for polynomial multiplication that is vital for fast implementations of Kyber and Dilithium. Chapter 1 is comprised of 2 video lectures. V1a gives a brief overview of the field of post-quantum cryptography. V1b will introduce some mathematical prerequisites for Kyber and Dilithium, including rings of polynomials and modules of polynomial vectors. If you are familiar with the field of post-quantum cryptography, feel free to skip V1a and proceed to V1b. The idea to use the weird and counterintuitive properties of quantum mechanics to compute things was proposed independently by the mathematician Yuri Manin and the physicist Richard Feynman. These weird properties include superposition, interference, and entanglement. I certainly don't have the time in this course to explain how quantum computers work, but I'll briefly give you a sense of their potential power and their limitations. The quantum analog of a classical bit is a qubit. Unlike a classical bit, a qubit can be in 2 states, 0 and 1, at the same time, each with a certain probability. This is a phenomenon of superposition. More generally, an n-qubit register can be in all 2 to the n 01 states at the same time, each with a certain probability. The potential power of quantum computers arises because when a function f is applied to an n-qubit register, in 1 unit of time, the function is simultaneously evaluated at all 2 to the n states. In contrast, on the classical computer, the function would be evaluated on each state 1 at a time for a total time of 2 to the n units. This capability makes quantum computers at first glance look like massively parallel machines. However, this is very misleading, since one is not able to view the result of applying f to all the 2 to the n states. Instead, when the n-qubit register is measured, it reverts to one of the 2 to the n states according to its underlying probability distribution. So what can be viewed as f of x, where x is only one of the 2 to the n states? And you don't get to select x, but instead it is determined by the underlying probability distribution. The challenge, then, in designing algorithms for a quantum computer is to exploit properties of superposition, interference, and entanglement so that at the end of a computation, the state that gives the solution to a problem occurs with probability very close to 1. And so, when the qubit register is measured at the end of a computation, with probability very close to 1, it reveals the desired solution. The potential power of quantum computers was highlighted in 1994, when Peter Shor discovered a polynomial time algorithm for factoring integers, computing elliptic curve discrete logarithms, and computing ordinary discrete logarithms. These 3 problems are the basis for the security of all RSA, elliptic curve, and discrete log public key cryptosystems. And so, all public key cryptosystems that are used today can be totally broken by Shor's algorithm on quantum computers. This is the main threat of quantum computers. The second threat of quantum computers is Grover search, discovered by Grover in 1996. Suppose that f is a function from the set of binary strings of length n to the set 0, 1. Suppose also that f is efficiently computable, and that f of x equals 1 for exactly one input x. The challenge is to find the input x such that f of x equals 1 given only oracle access to f. So you are not given a description of f, but just the means to evaluate it efficiently. Naively, you can solve the problem by selecting arbitrary x and computing f of x until you encounter an x for which f of x equals 1. However, the expected running time of this naive algorithm is about half times 2 to the n evaluations of f, because you can expect to try about half the inputs before you encounter the desired x. Grover search is a quantum algorithm that can find the x satisfying f of x equals 1 in only square root of 2 to the n evaluations of f, a quadratic speedup. Grover search can be used to speed up exhaustive key search on block ciphers such as AES. Consider AES with an L-bit key. The choices for L are 128, 192, and 256. Suppose that we have T known plaintext ciphertext pairs, MI-CI. The MIs are plaintext blocks, and the CIs are their encryptions using a secret key. The number T of plaintext ciphertext pairs is chosen so that the expected number of false keys is very close to 0. A false key is a key not equal to the secret key that encrypts the plaintext MI to the ciphertext's CI. Now define the function f from the key space 201 by f of k equals 1 if the key k encrypts the T plaintext mi to the T ciphertext ci, and define f of k to be 0 otherwise. This function f satisfies the two requirements for Grover's algorithm. So Grover's algorithm can find the secret key in the square root of 2 to the L operations, which is substantially faster than exhaustive key search, which takes 2 to the L operations. To circumvent the threat of Grover's algorithm, one should use 256-bit AES keys, since 2 to the 128 quantum operations is an infeasible amount of work even for quantum computers. The big open question is, when will quantum computers be built, if ever? Proof of concept quantum computers have been built, beginning with a 2-qubit machine by Jones and Mosca in 1998. In recent years, many large organizations have joined the race to build large-scale quantum computers, including IBM, Microsoft, Google, Amazon, and Intel. Also, many countries have been funding national efforts in quantum computing. Although there has been tremendous progress on some fronts, overall progress has been very slow. In December 2023, IBM announced a 1,121-qubit quantum computer. Factoring a 2048-bit RSA number using Shor's algorithm will require a quantum computer with at least 2048 qubit registers. Most importantly, these qubits have to be fault-tolerant, since the qubits will suffer from a phenomenon called quantum decoherence, whereby the qubits interact with the environment and errors are introduced. It's important to note that the physical qubits that have been built so far are not sufficiently fault-tolerant. And this is why existing quantum computers are not capable of factoring large numbers using Shor's algorithm. In fact, as of August 2024, the largest number factored using Shor's algorithm on a quantum computer is the number 21. I should note that larger numbers have been factored by quantum computers, such as D-Wave's machines. However, these implementations did not use Shor's algorithm. Instead, they solved related optimization problems using algorithms that don't scale to factoring numbers of cryptographic interest. Researchers have been designing quantum error-correcting codes, whereby many imperfect physical qubits are combined to give one logical qubit. A fraction of the physical qubits are measured every couple of hundred nanoseconds, and then corrected. In this way, the collection of physical qubits can be used to represent one logical qubit that is almost perfect. It has been estimated that several thousand physical qubits will be needed to build a single logical qubit. So factoring 2048-bit RSA moduli using Shor's algorithm on a quantum computer might need millions of physical qubits. It's too early to predict with any degree of certainty when large-scale, fault-tolerant quantum computers will be built. The next major milestone is to build a single logical qubit. Now, there have been some breakthroughs in quantum error correction in recent years, most notably by a research group at Harvard, MIT, and QEra. Nonetheless, it appears that we are still very far away from being able to break RSA and elliptic curve cryptography on a quantum computer. On the other hand, there is no fundamental reason why a large fault-tolerant quantum computer cannot be built. So it isn't at all clear how seriously one should take the threat of quantum computers. Certainly, if large-scale quantum computers can be built, then most of Internet security will be compromised, including automatic software updates, which rely on signature schemes, and TLS, which relies on signature schemes, RSA encryption, and elliptic curve Diffie-Hellman. Moreover, organizations such as the National Security Agency are collecting and storing large amounts of Internet traffic right now. Even if this data has been securely encrypted, the NSA will have the ability to decrypt the data if and when they have access to large-scale quantum computers. So it's difficult to decide what we should do, if anything at all, to mitigate the threat of quantum computers, and also when we should take action. Interest in deploying quantum-resistant algorithms increased dramatically in 2015 when the NSA made the following announcement. The Information Assurance Directorate will initiate a transition to quantum-resistant algorithms in the not-too-distant future. Our ultimate goal is to provide cost-effective security against a potential quantum computer. We are working with partners across the U.S. government, vendors, and standards bodies to ensure there is a clear plan for getting a new suite of algorithms that are developed in an open and transparent manner that will form the foundation of our next suite of cryptographic algorithms. The NSA seemed to be suggesting that practical quantum computers were coming soon, and that they would soon be transitioning in the not-too-distant future from elliptic curve cryptography and RSA to quantum-safe public key crypto systems. The NSA announcement caught a lot of cryptographers by surprise, and there were several theories and speculations about the NSA's motives. You can read about some of these theories in an article I wrote with Neil Koblitz in 2015. In response to the NSA announcement, NIST began a global effort to standardize quantum-resistant cryptographic algorithms for signature schemes and for key encapsulation. In 2017, there were 69 submissions from teams around the world. After extensive scrutiny by cryptographers, NIST selected 26 of these submissions in 2019 for further consideration. In July 2020, NIST selected 7 of these submissions for the next round of study, and also 8 alternative candidates. In July 2022, NIST selected the key encapsulation scheme Kyber and signature schemes Dilithium, Falcon, and Sphinx for standardization. The signature schemes LMS and XMSS had already been standardized in NIST's special publication 828. Finally, in August 2024, NIST published 3 standards: FIPS 203 for Kyber, FIPS 204 for Dilithium, and FIPS 205 for Sphinx. Another major development occurred in September 2022, when the National Security Agency announced Suite 2.0 of their Commercial National Security Algorithms, CNSA. This suite of cryptographic algorithms is intended for U.S. government use for protecting unclassified data, sensitive but unclassified data, as well as classified data. CNSA 1.0, which is NSA's current suite of cryptographic algorithms, specifies ECDSA and RSA for signatures, and elliptic curve Diffie-Hellman and RSA encryption for key establishment. CNSA 2.0 replaces ECC and RSA with Dilithium for signatures and Kyber for key encapsulation. It also specifies the signature schemes LMS and XMSS for software and firmware updates. Dilithium and Kyber are lattice-based schemes, whereas XMSS and LMS are based on hash functions. The symmetric key algorithms are unchanged, so AES for symmetric key encryption and SHA for hashing. The NSA also published a timeline for U.S. government adoption of CNSA 2.0 quantum-safe algorithms. The timeline for this transition to quantum-safe algorithms is surprisingly short. For example, NSA requires that quantum-safe signature schemes for software and firmware signing be implemented by 2025, which is next year, and be in exclusive use by 2030, which is only 6 years away. Also, NSA requires that web communications, in other words TLS, and cloud services such as Amazon's AWS, employ quantum-safe cryptography by 2025 and be in exclusive use by 2033, which is only 9 years away. These timelines are rather aggressive, especially taking into account the very slow advancement of the main threat to existing cryptography, large-scale, fault-tolerant quantum computers. Nonetheless, many governments around the world are promoting standards for quantum-safe cryptography, and industry is beginning to deploy quantum-safe cryptography in their products. Several large companies have experimented with deploying quantum-safe crypto systems in TLS. Among these companies is Google, which already uses quantum-safe cryptography to protect data in transit within Google's servers. Google is also working on including quantum-safe cryptographic primitives in their cryptographic library Tink, which is available on GitHub. In September 2023, Signal, the makers of the Signal protocol that is used in the Signal messaging app as well as in WhatsApp, added quantum resistance in hybrid mode by incorporating a shared secret key obtained using Kyber, along with shared keys derived using elliptic curve Diffie-Hellman. For further details, see the PQXDH protocol. In February 2024, Apple announced that their iMessage app had been upgraded with quantum-resistant cryptography in hybrid mode. My colleague, Douglas Stebla, did a security analysis of iMessage's quantum-safe key establishment and rekeying, which you can read about in this paper. To conclude this lecture, let me mention some of Amazon's initiatives with post-quantum cryptography. Amazon's Bracket program offers free use of experimental quantum computers manufactured by several companies. Amazon's implementation of TLS, called S2N TLS, which is available on GitHub, offers hybrid ECDH and Kyber key establishment. This hybrid mode is available as an option to current users of AWS cloud services. Amazon also conducts research at their AWS Center for Quantum Computing, which is located on the Caltech campus.